All right, so get this. Today, we're diving deep into particle physics.
Ooh, exciting.
Specifically, we're going to be looking at the hunt for the elusive top quark.
Yeah.
You've sent us some fascinating research about a new method for actually identifying these particles.
That's right. The paper's titled Finding Top Quarks with Shower Deconstruction.
Okay.
And it's a really, really innovative approach to this challenge.
Now, I have to admit, when I first glanced at this paper, it looked pretty intense.
Right.
Even for someone who enjoys keeping up with science news, this was next-level stuff.
Yeah.
So where do we even begin?
Well, imagine trying to find a specific bird song in the middle of a dense, noisy rainforest.
Okay.
That's kind of what particle physicists are up against.
I'm intrigued.
Tell me more. So particle colliders like the Large Hadron Collider smash protons together at incredibly high speeds. These collisions produce a massive shower of different particles all mixed up in a chaotic mess.
Right.
The goal is to sift through all of that data and find evidence of specific particles like the top quark.
So it's about finding a very specific signal amidst a cacophony of noise.
Exactly.
And the top quark, that's one of the particles that they're trying to isolate.
Yeah.
What makes it so important?
So the top quark is the heaviest known fundamental particle.
Okay.
It's also incredibly short-lived, which makes it even harder to detect directly.
Right.
But studying it is crucial for understanding the fundamental forces and particles that make up our universe.
It sounds like finding a needle in a haystack while riding a roller coaster at the speed of light.
It kind of is.
So how do they even begin to tackle this challenge?
This is where it gets really, really interesting.
Okay.
They've developed this new method called shower deconstruction.
Shower deconstruction. I have to admit that name has me curious.
Yeah.
Is it as dramatic as it sounds?
It's pretty dramatic in the world of particle physics.
Okay.
So essentially when a top quark is created in a collision, it decays almost instantly into other particles. These decay products are like the top quark signature.
Okay. So instead of looking for the top quark directly, they're looking for its calling card, the particles it leaves behind.
Exactly. These particles cluster together in a specific pattern, forming what physicists call a fat jet.
A fat jet.
Yeah, imagine a shotgun blast pattern on a target. But instead of pellets, it's energy deposits in the detector.
Okay, I'm visualizing it.
Yeah.
But wouldn't other particle interactions also create these fat jets?
They do.
How do they know which ones are from top quarks?
That's the million-dollar question, and that's where shower deconstruction comes in.
All right, I'm hooked. Break it down for me.
Okay, think of it this way. Imagine taking a high-speed photograph of that particle shower, right as the top quark decays.
Okay.
Shower deconstruction is like analyzing that frozen moment in time to figure out what happened.
So we're talking about analyzing a snapshot of something happening insanely fast.
Insanely fast.
That's already blowing my mind.
And it gets even more impressive.
Okay.
Shower deconstruction takes that snapshot and breaks down the fat jet into even smaller components called microjets. By studying the arrangement of these microjets, researchers can determine the probability that they originated from a top quark decay versus some other process.
So it's like taking a blurry photograph and enhancing it to reveal details you couldn't see before?
Yes.
Like some high-tech forensics investigation, but on a subatomic scale?
That's a great analogy.
I like that.
To make this analysis even more precise, they developed a variable they call chi.
Chi.
Which is essentially a probability score.
Okay, so a high chi score means there's a good chance we're looking at the remnants of a top quark.
Precisely, a high chi value means a high likelihood of a top quark jet.
Okay.
A low value suggests it's probably from something else.
Got it.
In their simulations, they found a significant difference in the chi distributions for top quark jets compared to other background particles.
Okay, so chi is like their secret weapon for filtering out the noise and zeroing in on the top quark signal.
Absolutely. It allows them to analyze the structure of these particle showers with a level of detail we've never seen before.
Wow, amazing. This chi variable sounds like a game changer.
It is.
But did the researchers put this new shower deconstruction method to the test?
They did.
How did it perform compared to other techniques?
So they compared shower deconstruction to 4 other top tagging algorithms.
Okay.
Johns Hopkins CMS HEP top tagger and N-subjettiness.
Okay, let me guess. Those are all different methods for trying to identify top quarks from the debris of these particle collisions.
You got to think of them like different filters physicists use to try to separate the signal from the noise.
Right. And how did shower deconstruction stack up against these other methods?
To understand the results, we need to consider 2 things.
Okay.
Signal acceptance and background fake rate.
Huh?
Signal acceptance is how good a method is at correctly identifying a top quark jet.
Right.
Background fake rate is how often the method mistakenly identifies something else as a top quark jet.
So it's like a game of accuracy versus false positives.
Right.
You want a method that's really good at spotting the real deal and doesn't get fooled by imposters.
Yeah.
Exactly. You want high signal acceptance and a low background fake rate.
Right.
And in their tests, shower deconstruction consistently outperformed all the other methods.
Wow, that's impressive. What kind of improvement are we talking about?
So for the same level of signal acceptance, shower deconstruction achieved a significantly lower background fake rate compared to all the other algorithms.
Okay.
It was particularly better than Johns Hopkins and CMS.
So shower deconstruction is like having a super precise filter that lets in more of the top quark signal while filtering out more of the unwanted noise.
That's a great way to put it.
Yeah.
And it's not just about identifying top quarks. Shower deconstruction can also help us measure their properties more accurately.
Yeah, that's fascinating. What kind of properties are we talking about?
Well, in this paper, they focused on measuring the mass of the W boson, another fundamental particle that's produced when a top quark decays.
Hold on, I thought we were all about top quarks. Now we're
Mhm.
talking about W bosons. Are they related?
They are very much related.
The W boson is one of the particles a top quark decays into.
Right?
So by accurately identifying top quark jets, shower deconstruction can actually help refine our measurements of the W boson's properties as well.
So it's a 2-for-1 deal.
Exactly.
We get a better handle on top quarks and W bosons using this new method.
Precisely. And the more precisely we can measure these particles, the more we can learn about the fundamental forces that govern their behavior.
Okay, this is where my brain starts to hurt a little,
Yeah,
but in a good way.
it's exciting stuff.
We're talking about delving into some pretty fundamental aspects of the universe here.
Absolutely. And there's one more detail in the paper that I think you'll find really interesting.
Okay.
They tested shower deconstruction with different cone sizes for the fat jets.
Okay.
Remember we talked about how these particle jets are like a shotgun blast pattern?
Yeah, the cone shape of the energy deposits.
Right. So the cone size essentially determines how wide of a net they're casting when analyzing these jets.
So they were experimenting with how much of the surrounding particle shower they were including in their analysis.
Exactly. And here's the remarkable part. Shower deconstruction remained remarkably accurate, even when they varied the cone size.
So even when they changed how much of the noise they were analyzing, shower deconstruction was still able to pick out the top quark signal effectively.
You got it.
Wow.
This robustness to different cone sizes is really important because it suggests that the technique is less sensitive to the messy realities of actual particle collisions.
That's a really good point. It's like having a noise-canceling microphone that works flawlessly even in the middle of a rock concert.
Exactly.
So we've established that shower deconstructions is a powerful new tool, but what does it all mean? This all sounds incredibly promising.
It is.
We've talked about how effective this technique seems to be, but what does this mean for the future of particle physics? What are the broader implications here?
That's the truly exciting part. This isn't just about improving our ability to study top quarks. It's about opening up new avenues of exploration in particle physics
Right.
with a more refined tool like shower deconstruction. Who knows what other mysteries we might unravel?
It's like we've been given a more powerful telescope to peer into the subatomic world.
Right.
What previously seemed blurry and indistinct could now come into sharp focus.
Exactly.
What are the researchers most excited about?
Well, one of the most tantalizing possibilities is using shower deconstruction to search for new, undiscovered particles.
Oh, wow.
By filtering out the known particles more effectively, we might be able to spot subtle signals that were previously hidden in the data.
So it's not just about studying what we know, but potentially discovering entirely new building blocks of the universe.
Exactly.
That's incredible.
And beyond the search for new particles, this technique could help us refine our understanding of the fundamental forces that govern particle interactions. The more precisely we can measure these particles and their properties, the closer we get to answering some of the biggest questions in physics. How did the universe begin? What is the nature of dark matter and dark energy? These are just a few of the mysteries that particle physicists are grappling with.
It's awe-inspiring to think that by studying these tiny subatomic particles, we're gaining a deeper understanding of the vast universe and its origins.
It is pretty amazing.
But let's not forget all this research is based on simulations, right? What happens next?
You're right. The next crucial step is to apply shower deconstruction to real-world data from particle colliders like the Large Hadron Collider.
What?
This will be the real test of its effectiveness.
So it's time to take this show on the road and see how it performs in the wild world of actual particle collisions.
Exactly, and that's what makes this such an exciting time for particle physics.
Yeah.
We're on the cusp of potentially groundbreaking discoveries, and with tools like shower deconstruction, we're better equipped than ever to explore the universe's deepest secrets.
Well said. This has been an incredible deep dive into the world of particle physics.
It has.
We've explored the challenges of identifying top quarks, the ingenuity of the shower deconstruction technique, and the potential it holds for unlocking new mysteries of the universe.
Yeah, it's really cool stuff.
And for our listeners, remember, this is just the beginning.
Definitely.
As these new techniques are refined and employed, who knows what incredible discoveries await?
Who knows?
Until next time, keep those minds curious and never stop exploring the wonders of the universe.